friends. Good to see you. We're here in Unit 2. We're going to look at lessons 7 and 8 today. And we're looking at a couple different things. We've made our kind of jump to the second half of our unit, and we're really looking at these rational functions. Now, I want you to know what this rational means. Rational has the word ratio kind of at the core of it. It's that root word that we're looking at. And so anything that's a ratio is something that has a comparison about like what parts we're putting together, or one part compared to another part. Really, when we look at ratios, we're looking at things that are fractions. So something divided by something else. So this shouldn't be such a huge jump that this is where we're going to, considering where we have been looking here in Unit 5, or in Lesson 15, sorry, when we've been writing all of our polynomial division here as a fraction. So that's really what we're looking at, is how fractions or things being divided by another item can impact the graph and what they look like. And we're going to see a very different kind of graph than what we've seen before. Unit 2 so far has been a lot of polynomials. We've seen some graphs that look like this, but this time we're going to see some graphs in fractions that are going to look very different. So Lesson 17 starts by thinking about biking. And maybe you remember from science or your past classes that we have distance equals rate times time. Now this is a good place to start because that's what a lot of our rational functions may look something like this, because we can also rewrite these in different ways. So if I'm driving at a rate of, let's say, 10 miles per hour, it's pretty slow, but I'm doing that for 3 hours, I would go a total by multiplying my 10 miles per hour, 3 hours, I'd be going 30 miles for distance. Not only that, but we can also rewrite these by dividing by either one of these two components and finding something like distance divided by the rate equals the time, or distance divided by time equals rate. We're going to be using all of these kinds of different ways that we could rewrite the same formula. So Kieran's aunt plans to bike 10 miles. If she bikes, and so 10 miles is the distance that she's going. And we want to know how long, which means we don't know time, will it take if she is at an average rate of 8 miles per hour. Well, 10 miles of her distance divided by the rate of 8 miles means that when we're doing that, we would have 5, we could reduce that to 5/4, or 1.25 hours. So I know it's hours because that's what was our unknown, was time. So it would take us 1 hour and 15 minutes. Now, if she then changes her rate, we could do that same kind of calculation with any rate r. So that's really just looking at our distance, rate, and time. So this equation here, that if we change that r value, how long will it take, that would get our distance by itself. Now she's still going 10 miles, so that is our distance that we're going, divided by a different varying rate would then give us the amount of time it would take her. Let's say Kieran wants to join his aunt, but he only has 45 minutes to exercise. What will their average rate? So this time we know that the time is 45 minutes. Now 45 minutes out of 60 minutes is 3/4 of an hour. We can also think about that on a clock, right? The hands would go 3/4 of the way around for an hour of time if we're looking at 45 minutes only. So Kieran wants to join his aunt. He only has 45 minutes to exercise. What rate do they need to go in order to make that happen and finish on time? I'm going to actually write this as 0.75, right? Because that also means the same thing. 3/4 is 75 cents in a dollar. So they're still going to go the same 10 miles, but this time they're going at 0.75 is how much time they have. This is going to give us the rate. So this time we're looking at isolating the rate. How fast do they need to ride in a set time? So I'm going to use a calculator just to check this one out. 10 miles divided by 0.75 gives us 13 1/3 miles per hour. So their average rate that they would need to go would be about 13 1/3 miles per hour. So if we then can bring this to any t, we would have their 10 miles that they would be going for distance. We could adjust the time, the hours that they're going, and as we adjusted that time, the output would be rate. So we're seeing how we can use specific known values, but we can also substitute in variables and change that. So I think you see we might be going to x's and y's going on here. So let's see where we do go. 17.2 is setting this still at our distance, always a distance of 10 miles per hour in this example. So to write an equation that gives his time in hours, time, as a function of rate would look like this. When it's written like this, to give time as a function of rate, it's saying to get t by itself on one side of the equal sign. And our only variable should be the other one in terms of rate. So rate is their only other variable on the other side of the equal sign. It asks me to graph this. So I'm actually going to go look at a Desmos and I'm going to sketch my graph also here in my workbook. So here is my Desmos screen. And we are graphing 10 miles divided by an unknown x. And so this is the graph that we see here, and this is what we're going to sketch into our workbook. Now there are some parts that make sense and parts that don't, but as I zoom out, I see what this shape is looking like. So this is what we want to sketch in our workbook here. So I'm just drawing some of these ideas in. So we have rate is our x value, time is our y value. So just seeing that stuff starts to get us going like this. So this is what a graph that I sketched in my workbook, just to kind of start to see what some values would be that make sense. And the meaning of t of 8, well, let's see, that 8 here is in place of the r in my function notation. So what this is telling me is that at a rate of 8 miles per hour. Now I know it's rate because that's what place it's taking. The output of this would be the time. So it takes blank time to ride 10 miles. All right, so that's what it's telling me. When we have questions like this, we want to interpret the input and the output. We've been practicing this a lot throughout the year when we've been talking about how much the length of a side that we're going to cut out gives us the volume of a box, or length of a side for the area of a chicken coop or a play area or something like that. Now we did already calculate this one when we had a rate of 8 miles per hour. It's here in our warm-up. There it is. It took us 1.25 hours, or an hour and 15 minutes to do that. So it takes 1.25 hours time to ride 10 miles. So that tells us that the rate of 8 was here. We followed it up to the graph. We could follow it over and find out that it takes 1.25 hours. So it's nice to see that graph kind of in action as we go. So the meaning of t of 0, and does this value make sense? What this is saying is that we're going at a rate of 0 miles per hour. We're going nowhere. We are standing still. We're not even like walking forward. We're going at a rate of 0, nowhere at all. And when I look at that on my graph, this rate of 0, right? If my rate is, I haven't moved at all from the origin, as far as how much time is it going to take, this is actually gets closer and closer and closer to that axis, but it's never going to touch it. And here's why. If I'm not moving at all, if I'm going 0 miles per hour, I am never going to go 10 miles distance. I'll never get there. It would take me more than an infinite amount of time because it would never, ever even happen. So the meaning of t of 0, right, or a rate of 0, really what we're thinking is that we would have 10 divided by 0. 0 miles per hour as our rate. And when I try to do that on a calculator, you're going to get an error when we try that all day long. In fact, anytime we try to divide anything by 0, we're going to get an error message. We can't divide by 0. Even our fancier calculators are going to tell us that we can't do it. 10 divided by 0 gives me an error message. Okay? Calculation fails. So it doesn't make any sense in this context. We get an error message on our calculator because we can't divide by 0. We just can't do it. And it makes sense that if we're not moving, we will never go 10 miles. We'll just never, ever get there because we haven't even started moving in the first place. So let's see what happens kind of at the other extreme. We've talked about what happens as we're getting closer and closer this way, right, to that. As our rate gets slower and slower and slower, the time is going to take longer and longer and longer. So as r gets closer and closer to 0, as our rate gets slower and slower and slower, our graph is telling us that the time is going to take more and more and more and more and more time. That's what we want to express here. As the r gets closer to 0, as the rate gets slower, a smaller number closer to 0, it takes more time to get there. So as the rate gets slower and slower, a smaller number closer to 0, it takes more time to go 10 miles. As the rate gets larger and larger, meaning faster, a higher number, it takes less time to go 10 miles. Now we see that in our graph too. So as our rate gets larger, as our rate goes faster and faster, a higher number, it takes less time to go 10 miles. That makes sense. We see this as our rate gets faster and faster, as we get a higher and higher rate. Look at our time go down, 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 down. Now there will never be a way that we can go at a rate so fast that our time would be 0. We're never going to be able to go that fast. It would be teleportation. And we haven't invented teleporters yet. So we can't do that. What we have, and what I'd like you to write as an idea here, is that we have two items that are called asymptotes. asymptotes. We have two asymptotes in here. And the definition of an asymptote is a line or value that the graph gets closer to but never touches. So in this case, this graph is getting closer and closer and closer to this horizontal asymptote. This horizontal asymptote and that horizontal asymptote is the x-axis. That's telling me that y equals 0 because it hasn't moved up and down off of the axis. So as the rate gets higher and higher, it gets closer and closer to a time of 0, but it's never going to quite touch 0 because that would mean we're teleporting. Can't do it. Breaks the laws of physics. We also have this vertical asymptote. This vertical asymptote is happening right here on the y-axis in this case, and that is going through the x-axis. Our x hasn't moved side to side. We have a line right on x equals 0. Now, these horizontal and vertical asymptotes are directly related to our equation that we have coming up. And that's what we're going to add some ideas and notes here. So in lessons 17 and 18, our big idea is how do we find a horizontal asymptote and a vertical asymptote? And then we'll start seeing how we can put it into context, into some other situations. All right, so we have defined what an asymptote is. Next time I see you, we'll do this card sort that we're going to start looking that can match. But we'll also actually, they're in your cool down packet. And we'll take a look at those in just a second. But what I want to do is look at them this way. Our lesson summary, so I'm on page 190, starts to connect this vertical asymptote. Now the one that we saw was 10 divided by x. And it had a graph that looked like this, right by the x and y axes. Now, first of all, I do have to say, in our context over here, this part of the graph didn't make any sense. We're going to just ignore that. That's not actually part of our domain. Because that's saying if we go a negative rate, that would mean like I'm pedaling backwards or something. I don't know. Or a negative time, which means now we're inventing time machines, not just teleporters. Neither of which exist. So we ignore that part in reality. But those parts of our graphs really do exist. And when we had something with an x in the denominator that we said we can't divide by 0, our asymptote showed up at x equals 0. Now our example here on page 190 in the summary changes the denominator to be x minus 3. And notice that that changed the vertical asymptote. Do you notice how it's now moved over to the right at x equals a positive 3? So it's cutting through the x-axis at positive 3. And this is because if we plugged this 3 into this equation, we would have 1 over 3 minus 3. We would have 1 over 0. And we have this idea that this can't happen. This is our error message. So we are going to see a direct, not a direct, we're going to see a relationship going on from our denominator to the vertical asymptote. Now this is such a big deal and an important idea that I'm going to start my Unit 2 final help sheet for our final test. Unit 2, Part 2. And if we have something written something like this. So we're going to be seeing that we're going to have whole numbers and we're going to have fractions. Now this again should look familiar because this is how we've been writing the result of our division so far. We've been writing it with our result, our remainder, and our denominator. So these are kind of our three parts that we're looking at. And the big idea is that this denominator cannot equal 0. It's going to tell me the vertical asymptote every single time. So I'm going to put my note here that a denominator cannot equal 0. Whatever value this is that would make it be 0 is where my asymptote is going to be showing up. I have a vertical asymptote that is coming directly from this denominator. And it's happening in this case where x equals positive 3. So just like in the beginning part of our Unit 2, where we were changing factors to zeros and zeros to factors by changing the sign, we are seeing that changing that sign again still gives us some information here in rationals when we've got a fraction going on that it can't be a value. We're going to get an asymptote going on. And we're going to see that we can have more than one vertical asymptote at a time. It just means we would have more than one factor in the denominator at a time. So you can hit pause on this video right now if you want to start working on your lesson 17 practice problems. I see a vertical asymptote going on there, so that might be something good to look at, some information going on. But I'm going to also continue on through lesson 18. So maybe you want to keep on watching and filling in your work as you go, and then come back and take care of these two practice problems together. Now, when we start trying to rewrite equations, we have to be very careful about how we do this, right? Lesson 18 you see is that we're looking at horizontal asymptotes and how we can tell those things, all right? So if we have something like x plus 7 and we're dividing it by x, this is a valid way to rewrite it. And so I want to show you why that happens. A lot of times in your past, if you needed to add fractions, you knew you had to have a common denominator before you could add those fractions together. Here, we have already added those fractions over a common denominator, but I'm going to split them back apart because you may not see this as that idea of it being x over x. Now, I had to remember this when I was growing up, that before I was going to rip something apart into two separate fractions, I was going to give it a little bit of love first. So you're going to give a little bit of heart love here to your fraction, and then we can rewrite it in its two parts. X over x plus, because there's a plus sign in between there, 7 over x. Now, x over x, if we have the same thing in the top and the bottom of a fraction, if we have like 8 divided by 8, it's going to be 1. If we have a million divided by a million, or negative 17 divided by negative 17, that's where the 1 is coming from. So same thing in numerator, denominator, we can cancel those out and it's just a value of 1. So these two, they do check out. Now the same is not true the opposite way. We don't just selectively start canceling x's here like this because we just have a single numerator, x. And I'm trying to divide that whole numerator by the full denominator, x plus 7. So this is not valid, not true. So these we could add together because they had common denominators. That's how we could get back to where we started here. Common denominators means we can add the numerators together over that same denominator. Or if we keep them ripped apart like this, we can maybe simplify it this way. This is not true that same way. I cannot do x divided by x plus x over 7. It just isn't a valid way to do that. So just put that x through that and keep that in mind. We can put the same denominator under all parts of our numerator. Or we could also look at this as polynomial division. So far we've always set up a factor outside of our boxes, we put the numerator on the inside, and we'd be like, well, inside has to be x, and whatever happens over here has to equal a positive 7. Well, x times something to equal x, that has to be 1. It can't be anything else. There's no x squared or anything like that. And so now I have my constant. There's my result. But I still have this plus 7 that's like my remainder. So there's kind of another way to go about it. This is my result. We write it out by itself. This is my remainder. We write it as the numerator of our existing divisor. So just kind of a connection to something in the past. You'll see me just doing it a lot like this. Give it a little love. Rip that fraction apart. So 18.2 starts to give us some actual context, and now we're going to see that this thing has changed its horizontal asymptote, right? Our vertical asymptote is still at 0 here. So let's look at this and the equation that we have. C is a function that gives the average cost per book in dollars when using an online store to print X copies of a self-published book. So let's say I wrote a great book. I want to publish it. I can't find someone who'll do it for me. So I'm going to pay my own money to have it published. And so it looks like there's like a flat fee set up to get ready for this publishing, and then $4 per book. There's my total cost on top. And if I divide it by the number of books that I'm getting printed, it tells me how much I'm paying per book to get this thing published. That's nice, because then I know how much I should charge so I can make a profit. Okay. Now this x denominator is just x, and we know that x cannot equal 0. The denominator cannot equal 0. So we have a vertical asymptote at x equals 0. But what's interesting in this graph is that it looks like our horizontal asymptote has changed. It's no longer the x-axis. It's here at y equals 4. And so we want to find out where that horizontal asymptote came from. How did it change? So let's look at our couple questions here first. What is the approximate cost per book when 50 books are printed? Well, let's take a look at our graph and kind of approximate that. 50 books. Follow it up until you hit the graph. Follow it over then to figure out our cost per book. And it looks like it's about, I don't know, maybe $6.50. Now, that was our estimate from the graph, but we could calculate the exact amount. All right, so let's plug it in up here. If we know that our X is $50 or 50 books, if we had 120 plus 4 times 50 books that we're going to publish, there's our total cost. And then we divide it by 50. Now be careful on your calculator. You can't enter this all at once unless you're using parentheses, because your calculator won't know what to do with it. So I'm going to do my total cost. 120 plus 4 times 50 books that we are going to publish. Oops, what did I do? Oh, I just had 2. There we go. And so my total cost is $320 divided by the 50 books that I'm publishing. We find that it's actually $6.40 per book. All right, so my estimate from the graph was pretty close, but it's going to actually cost me $6.40 if I publish 50 books. Now, if I publish 100 books, I can just change that X to equal 100. And so we have $120 plus $4 times 100 books divided by 100 books. So I can find the price per book. We're looking at 120 plus 4 times 100. Get your grand total, and then divide it by the 100 books. So we can find out that it's $5.20 a book. We can check that on the graph too. 100 books, follow it up. It hits right about here. And yeah, that's about $5.20. So that looks good on my graph as well. Verified and checked. Now, if an author plans to charge $8 a book, just seeing where we were going, sorry, $8 a book, how many should they be printing? Well, this means that we're back to not knowing how many books. So I'm going to use my original equation with my unknown x's, and I want to have it equal to $8. Now my graph tells me if I take that $8 per book, follow it over and then down on my graph, I might be looking at somewhere around about 35 books, but I can get exact by here. Now to solve this, we could do a couple different things. My favorite way to solve these is to multiply both sides by x, by the denominator. So multiplication and division cancel each other out, and we're left with 120 plus 4x equals 8x. Now we can subtract 4x from both sides. We're just getting all of our x's to one side and all of our constants to the other. 120 equals, these will cancel. 8x minus 4x is 4x's. Now I have one last step in order to solve this for x. To figure out how many books we would need to print, we would have to divide by 4. Those 4's here will cancel out. So x equals 120 divided by 4, which is 30 books. Pretty close to what I predicted from my graph. Now the value of c of x when x is 1/2, and how does that relate in our context? It's kind of a strange question, isn't it? And x is 1/2. It's saying that we're going to print 1/2 of a book. And it does not make sense to do that, right? In our context, it doesn't make sense. But we could still calculate the value of that. 120 plus 4 times 1/2 of a book divided by 1/2. So 120 plus half of 4, so 2, right? And 120 plus 2 is 122. Divided by 0.5. It would cost us $244 to print 1/2 a book. It just doesn't make sense. All right, so what it tells me that is that the end behavior of the function, what does it say about the context? And really a better way to put this is how could we better see the vertical asymptote? I'm sorry, the horizontal asymptote. So I'm going to do that 120 plus 4x divided by 4, or divided by x. Excuse me. That's our original equation. I'm going to rip it apart into 2 fractions, so I need to give it a little bit of love first. $120 divided by x plus 4x over x. You see what can cancel out and what can simplify here? These x's multiplying by x and dividing by x. So x would go into this 4 times evenly with a remainder of 120 over our original divisor of x. Now, we already know that the denominator is where our vertical asymptote is coming from. I'm going to shorthand that as VA for a vertical asymptote. But do you remember up here where I said this thing has a horizontal asymptote at 4? This positive 4 is the gotta get it right, horizontal asymptote. And it's direct. We don't have to change the sign. We don't have to do anything wacky to it. We don't have to do anything else. So whatever the result is of our division, we're going to get an asymptote happening there. And then whatever is our denominator, we've got a vertical asymptote happening there. So this one has just a 4, comes out evenly. That is what's making that horizontal asymptote of 4. I'm going to go back to the notes that we had at the back of the book that we just added. And I just want to have this idea that the result of our division is, if it's just a number by itself, it is our horizontal asymptote. And it is horizontal, so it's going to go through the y-axis, and it's going to be the exact number that we see there. So if it's a negative number, we'll have a negative horizontal asymptote. This is a positive 4, so we have a positive 4 asymptote. So it's kind of neat to see where those things are coming from in the equation and how we can start to see them in the graph. This means that the more and more books that I publish, the closer and closer the price per book gets to $4 each. So if I start printing like 400 or 500 books, if I charged $5 a book, I would be making a profit. Now, this graph will never go below $4 per book. So even if I ordered like 10 million of these things, it would never go below $4 a book. I can't get it cheaper than that. So here's our last part of the lesson here, and then I'll set you free to go do some practice problems and see how we're doing with it. It gives us in 18.3 4 graphs of some rational functions, and it asks us to match each of these to A, B, C, D, E, F, G, H, right? And seeing the horizontal asymptote. So we're going to do some practices here, all right, and see where these things are showing up. So first things first, I see down here, I'm going to start doing some circles and some ideas going on here. All of these have an x, a denominator of x. So they all have a vertical asymptote of x equals 0, okay? And none of these can x equal 0. So I'm just going to kind of put that little note here that all of them, every single one of them, x cannot equal 0, and all of these are our vertical asymptotes. So I'm mostly focused here on my horizontal ones, the ones that are going left and right. So we said that if there's a number outside the fraction, whatever that is our horizontal asymptote. So I'm looking for a horizontal asymptote at y equals -1. It's a -1 sign, so I'm looking for a -1. And when I look at that, it is happening right above it here in graph D. So this is going to, part A is going to match graph D. And so I'm going to be like, all right, A is that graph. Now our next one down in that same way is at -4. So it's got a horizontal asymptote. Again, I'm going to just shorthand that as HA at y equals -4. Now that -4, when I'm looking at my horizontal, let's see, this one's at a +1. This one's at a +4. This one's at that -4 that I'm looking for. So it looks like graph B is matching with our equation B. I'm going to put that up here too and be like, hey, that's going to match this guy here. Now our next one isn't written in this 2 separate fractions kind of thing. So I'm going to make it. Right? We know how to do division, or we can just use that, rip it apart, give it a little bit of love first and rip it apart. Another way we could write this is 1 over x plus 4x over x. Multiplying by x, dividing by x cancels out. 1 over x plus 4. Bazinga. Horizontal asymptote at y equals positive 4. And that is matching graph A. We already said that that horizontal line is going through there. So I'm going to put graph C, equation C up there is matching that, and matching C with graph capital A. I'm just going to work through the rest of these so I can keep on seeing some more of that, giving it a little love. X over x plus 4 over x. X over x is the same as 1. Here is my horizontal asymptote at y equals 1. And that is matching with part C, graph C, graph C. Couple more to work on here. E, again, I'm going to give it two separate fractions, 1 over x minus 4x over x. X's cancel out. So we're just kind of working in silence here, but just getting lots of practice. So we can start looking at these equations and identifying whatever's outside the fraction, horizontal asymptote. It's a y equals because it crosses the y-axis. This one's a positive 1, so I'm looking at this where the y value is at positive 1. G, graph C, good match. And last but not least, a positive 4, horizontal asymptote. H would be there, so that's graph A. All right, so when we are able to do the division, it's whatever part is not in the fraction that's going to be our horizontal asymptote. Graphs A matched up with equations C and H, graph B with equations B and E, graph C with equations D and G, and graph D with equations A and F. So we can start to see some pretty neat stuff going on. So again, that's got a good little refresher that we can start to see what those horizontal asymptotes would be at 3 or negative 3 and how we can start to find those and which one is which. So your goal now is to complete practice problems in lessons 17 and 18. When I come back, we will do a graph matching activity that will be looking at these horizontal and vertical asymptotes. Thank you, friends.